Namaste, everybody. Today, in a TAI seminar series, we have the topic spatiotemporal deep learning models for detection of rapid intensification in cyclones. This is a very special project. I will tell you a bit of background about it, but firstly, let me introduce you to Vamshika Sutar, who is leading this project, and Amandeep Singh, who was part of this project, and he did contribute significantly before he left the project and he joined the industry. And Vamshika is a graduating student from IIT Bombay, and Amandeep has graduated from IIT Bombay. So towards the end of the COVID era, this probably more than around 2 years ago, Amandeep did an internship with me, and there we this was the project. So why is this project important? So actually, I moved into the area of cyclones with machine learning around in towards the end of towards 2015, back when I was in Fiji. And so we were doing this project, and the work that was done in this project, we did not really get the time to complete it. So it was on hold. So I have other collaborators in this project. And they contributed, but we were not satisfied with the results. So it was on hold for almost 10 years. And then finally we met Amandeep, and then he was quite enthusiastic and he really contributed to the coding parts. And then Vamshika continued from there. So I would let Vamshika continue with the presentation, and I would begin by thanking them in advance that thank you for making sure that this project is complete. It took around 10 years to do so. Thank you, Vamshika.
Thank you, sir. So we'll begin with the introduction part. And the basic motivation for this paper comes from the cyclone rapid intensification phenomenon, which is a phenomenon that occurs in tropical cyclones. And it is defined as a sudden increase in wind intensity exceeding 30 knots within 24 hours. And it reduces a warning time and leads to severe infrastructure damage, and also forecasting challenges and heightened economic and climate related risks. So this is an rare event, and it creates a lot of class imbalance in the data set. By class imbalance, I mean that there are a lot of cases in the data set where the rapid intensification is not occurring, and there are very few cases where it is occurring. So it becomes difficult for the machine learning models to actually learn to classify the event. So for that, this also we have in the data set, we have used time series data set where data is wind speed, features like latitude, longitude, or wind speed are taken on a time series basis. So LSTMs are known for their ability to learn temporal patterns in data. So we will see if they can help in detection of this phenomenon. So the objective of this paper, what we have basically done in this study is we propose several deep learning frameworks, I mean different variations of LSTMs, and some data augmentation framework as well to address the class imbalance problem. And then we use LSTM only to generate synthetic cyclone data, unlike common methods like SMOT or using GANs to generate synthetic data, so that it is more representative of the original data. So basically, yeah, this is the basic introduction for this paper. And coming to the datasets part, we have considered the equatorial region in the southern hemisphere because it provides optimum conditions of temperature and pressure for formation of cyclones in the region. And we consider South Pacific Ocean and Southwest Indian Ocean as basins of interest. The data was extracted from joint Typhoon Warning Center, JDWC website, and we used data of the tropical cyclones from 1980 to 2020. And these were the basic features used for the ML models, latitude, longitude, and wind intensity. Also, it was a time series data where each data point, difference between two data points was 6 hours. So 4 data points made up to 24 hours. So coming to some basic uh, uh, analysis on the tropical cyclones over the years, we can see that we can see the cyclone frequency over the years for the two basins. This is for the South Indian Ocean. Cyclone frequency is high, as we can see, around the year 2000. And for South Pacific Ocean as well, it is high around 1995 to 2000. So yeah, this is it. So it is the high. We can see the cyclone activity is highest in these time durations. Uh, Just a minute. Okay. Coming to the RI events and tropical cyclones over the years, we see this now we compare the frequency of RI events over the years. And for the South Indian part, we can ocean as well, we can see the RI events are high in these years, 1995 to 2005. And for the South Pacific Ocean as well, it is high somewhat more in between 1990 to 1995 as well compared to South Indian Ocean. And here also it is more between 1995 to 2005. So coming to cyclone, categorizing the tropical cyclones in different categories. So we classify them based on wind speeds. So less than 33 knots comes in category 0. And yeah, some 34 to 47 knots, it comes in category 1. And from 48 to 63 knots, it comes in category 2. Yeah, and greater than 116 knots comes in category 5. So this is having category 5 is having the highest wind speed. This is another histogram which shows the RI events within each cyclone category. So we can see that the RI events are rapid intensification events are highest for category 4 cyclones, and next comes category 3. And this is classified based on the two ocean basins as well. So we can see that the number of cyclone events are more naturally for South Indian Ocean. So there are more such events in that ocean. So this is another plot which shows insight into cyclones in South Indian Ocean basin. So the blue tracks, as we can see, represent the non-RI cyclones where that phenomenon or the rapid intensification phenomenon has not occurred. And the red ones show the RI cyclone events or where it has occurred. So we can see that there are the blue cyclones are much larger in number compared to the red cyclone tracks. So this is another plot where the cyclones are categorized based on different categories based on the wind speeds. So we can see different cyclone plots. We can also observe that the category 4 cyclones, which are the red colored cyclones, are mostly in this area in the middle part. And category 1 and all are also are quite distributed throughout the plot. Coming to the methodology section. So this is the basic framework of the entire paper, what how we have processed the data and our methodology part. So firstly, we take the data of the cyclone events, and then we do data analysis and cleaning. And then we extract the RI cases based on the change in wind speed greater than or equal to 30 knots in 24-hour duration. And then we do data augmentation using a multivariate LSTM. And then we combine real data and synthetic data to create the training set. And then we use another multivariate LSTM for classification. And then we get the results and analyze them. So these are 4 different LSTM models that we have proposed. They are independently trained on the original data set without augmenting it to get the baseline results. So firstly, we have the univariate LSTM, which is just trained on wind intensity. And secondly, we have the multivariate LSTM, which is trained on wind intensity and also on latitude and longitude features. And then we have an ensemble of LSTMs, which has 3 different LSTMs in it, each one trained on a different feature. Suppose this LSTM is trained on wind intensity, the second one is trained on longitude, and the third one is trained on latitude. And we can see that we use a voting classifier in the end to get the final prediction. And then we have a hybrid ensemble LSTM, which has 2 LSTMs stacked together. One is trained just on the wind intensity, and the second one second is a multivariate LSTM, which is trained on 2 features, longitude and latitude, and we stack the results to get the final prediction. Yeah, this is the description of the 4 LSTMs as I have shown above. So firstly, we have the univariate LSTM, which takes only wind intensity. Then we have the multivariate LSTM, as I described, which takes wind intensity along with the spatial coordinates. And third one which combines output from multiple ULSTMs trained on different features. And finally, it's the hybrid ensemble LSTM, which integrates both the univariate and multivariate LSTMs. So this is the experimental setup for both the baseline models and for the data augmentation model. We have used the ReLU activation function, and we have used 50 hidden layers. And for output neurons, we have used softmax, and we have used 2 layers, and then we have trained using 100 epochs. It is the same for the data augmentation LSTM as well, but loss function is different here. We have used mean squared error loss function, since it is going to be it is not a classification result. It is the wind speed and latitude, longitude, those points are actually being predicted. So this is another data analysis part. And in the South Pacific Ocean, we see that the number of instances in the training set are 7,272 instances, and minority class is just 5% around. And the test set is 2,424 instances, and it's just 1% of it are rapidly intensifying. So it is a case of severe data imbalance. And same goes with the South Indian Ocean as well. The numbers are pretty small. The minority class is just 4% around in the train set, and just 2% in the test set. So this is a close look into the data augmentation framework. Firstly, we take cyclone tracks, which are actually rapidly intensifying. And then we use an LSTM model and predict some more data points of those cyclone tracks so that we can add them to it. So basically what we are doing is we are having a multivariate LSTM that takes in 4 time steps of spatiotemporal data, also the wind speed, and predicts the next 4 time steps. And then we join them together to get an 8 time steps of cyclone instance. And that is synthetically generated, and it is added to the train set. So as we can see here, the blue points are first the 4 time steps that we already have, and these red points are being predicted. And these are the longitude and latitude coordinates. I've shown for 6 different instances like that. So next, we see the average wind speed. We see some histograms for after the data augmentation part. So we have plotted some histograms. Here we can see average wind speed. Like suppose we have here 8 data points, right? We take average wind speed of all of them. And then we plot for the original data set, the rapidly intensifying data set, and then the augmented data set as well. The original data set has these blue bars, and the augmented data set are represented by these orange bars. And we can see the number of samples. So this is for the South Pacific Ocean. And we can see that there has been increase in number of samples. That is why the frequencies of the orange bars are more. So here also for the South Indian Ocean as well, we have plotted the same way. We have increased a lot of data points in this region, 40 knots, 60 knots here also as well. Then the experimental setup for data augmentation model. We use Adam optimizer, and we have run it for 100 epochs. We have used for the augmentation LSTM, we have used mean square error as mentioned before. And next for the classification LSTM, we have used cross entropy. We have evaluated using precision recall and F1 scores. Two types of F1 score, macro average and weighted average. And we have done 30 independent runs for the confidence intervals. Then coming to the results part. So this is the results of the baseline models, the 4 LSTM models that I initially said, without when they are trained on the data set without data augmentation. So this is for the South Pacific Ocean. If we have a close look at the F1 scores of the RI for the rapidly intensifying cases, then we can see that the HE-LSTM is performing best among the others. Its F1 score is highest, and next comes the ELSTM, the ensemble LSTM, and then comes the ULSTM. And then for the South Indian part, we see that the best performing model is the multivariate LSTM. And then we see that the univariate LSTM is performing best in this case for the baseline model. Next, if we see the results for the data augmentation using after adding the augmented samples and then training the classification model again, we see there's a significant improvement in the F1 scores. So firstly, if we look into this is the MLSTM without data augmentation. DA-MLSTM represents the MLSTM trained on the augmented training set. So for the South Pacific Ocean, there is a significant increase in the final F1 score. So it is from 0.339 to 0.65. And for the South Indian Ocean as well, there is significant increase in the F1 score. We see significant increase in macro average and weighted average scores as well. So the data augmentation is actually helping the model to learn better and distinguish between the non-RI and RI cases. Coming to the discussion part, our results indicate that adding spatial coordinates improves the accuracy of the LSTM models. Also, we see that HLSTM performs best in South Pacific Ocean, as we have seen, and MLSTM performs best in the South Indian part. This is a rare and extreme event. That is why we needed to do data augmentation. So our data augmentation methodology, we used LSTMs because we had to generate even the spatial coordinates along with wind speed. So that is something should be representative of the original data. But if we use GAN or SNOTES, it will be, the tracks will be something random and not very representative of the original data. And MLSTM, when trained on augmented datasets, provides improved results, as we have seen in the previous slide. So coming to some limitations of this work and some paths for the future work, we have not included features such as air temperature or air pressure, which are actually crucial for rapid intensification of tropical cyclones. And we encourage the future research endeavors to prioritize including these features into the framework. And these benchmarks that we have provided for the models trained on the original data set and the models trained on the augmented data set, they provide a benchmark for future research aimed at improving the detection of or exploring an alternative model architectures. So coming to conclusion, the LSTM, the original LSTM framework addresses class imbalance. These are new models, LSTMs, especially ELSTM and HELSTM. There are something novel and something new LSTM frameworks that will look into the detection of cyclone, rapid intensification in cyclones, and trajectory features like latitude and longitude will improve the prediction accuracy. Data augmentation has significantly improved the accuracy in like F1 scores, precision, and recall metrics. And coming to the references, we have this code. We have the link to the code and the data sets as well. We will have a short, we'll just go through the code for a minute. We will go through the multivariate LSTM code. Here we can see that this is a code where here we have splitted the cyclones into different categories, and then we have the code to load the data sets, and then we load the data frame for the cyclones with different features. We have the speed, latitude, and longitude as well. And then we have these different hyperparameters defined. We have the n steps in a 6, and we have taken 6 time steps to the LSTM. And we have the 3 features taken, latitude, longitude, and speed. And we have considered one hot encoding for the classification part. And we have used 50 hidden layers, 100 epochs, and we have run it for 30 experiments. And this is all the data processing part. And we go to the code. This is the MLSTM that we have defined. So yeah, we have used the ReLU activation function, and then we have used a softmax for the output layer. And then this is the code for running LSTM, processing the data and running LSTM. We only have one LSTM, and yeah, this is the code for running it, code to run it. And it loads the data from the cyclones, and then it runs it. Yeah, finally we can save the model with weights, and then this is making the confusion matrix, and then finally we can see the results as well. This code is to display the results. So we'll look into other LSTMs as well. Again, it's the same framework. We are importing different libraries, and then we have categorized the cyclones. And yeah, we have processed the data, and we define the different parameters here. Input time steps, as we have taken 6 time steps, and hidden layers are 50. And we have used the same 100 epochs, and we have run it for 30 experiments. This is all the data pre-processing part. We have ensured that the RI window is for 24 hours only, and it is classified that way. We have done the train test split here.
Thanks, Vamshika. Uh, Thanks, Vamshika. Could you probably go into the data augmentation part?
Yes, so I'll do that.
That is probably a major contribution as well.
Yeah, I'll directly go to the LSTM codes. Yeah, so this is the LSTM codes for the data augmentation model. And firstly, we take 4 time steps, and then we predict the forward upcoming time steps. We take in 3 input features, and then we output 3 of them. We take in the wind speed, latitude, and longitude. And we have used the Adam optimizer and mean squared error. So this is the code to run it, and then yeah, it predicts the 4 time steps, as we can see, in both in the test set and train set. Later, it is combined to the original 4 time steps to create synthetic signals. So this is how it works. So there are also links for data set as well. And yeah, I'll
Okay,
be
thank
happy
you,
to answer
Vamshika.
any questions.
Thank you, Vamshika, for a wonderful presentation. Okay, we can take questions. Any questions on the floor? Are there at this at UNSW at the Red Center? Any comments from UNSW listeners? All right. Online questions.
Vamshika, just
Ratanil, you
a
have a question?
question. I'm not sure you are the right person to answer this, but why LSTM for augmentation? What was the rationale for using LSTM?
Okay, so LSTMs I used because we had to augment that we are using the multivariate LSTM for classification, right? So it needs even the drag information like the latitude and longitude information along with the wind speed. So if we use this mode or GAN, it will generate some random track information which may not be representative of the original cyclones. But LSTMs, when we have trained it using the mean squared error loss function, it will generate similar tracks compared to the original data set. So that will be more representative of the uh, original data set, we thought. That is why we implemented LSTMs for data augmentation.
Maybe I missed this in presentation, but did you have a distribution of your original data versus your synthetic data?
Yeah, we had that. We had a histogram showing.
Okay, sorry, yeah, maybe I just missed it.
I think it is visible here if you can see it.
Oh, yeah.
I just want to add that typically, like for data augmentation, LSTM is not used. This is quite unique, and as because the application is unique, it's a spatiotemporal problem, and we have a review paper where we have reviewed data augmentation methods for class imbalance problems and ensemble learning combined with ensemble learning. And there you can see, even in the review paper, LSTM is never used because for the class imbalance problems, we are looking at tabular data. For example, you have iris, wine classification, but you have a bit of class imbalance there. But the problem we have here, rapid intensification, this is an extreme class imbalance problem. But then the data set is not tabular, it is spatiotemporal data. So we're looking at So yeah, when you're looking at a cyclone, you have an event maybe for a week. It can even last for 2 weeks. But then rapid intensification, the definition is when the wind intensity becomes more than 30 knots within 24 hours. So we need to keep on basically monitoring the wind intensity. And the data that we had is every 6 hours.
Yes.
So that basically gave that there was a lot of bias in. I mean, rapid intensification events are more rare in cyclones, and we have presented the statistics about that.
Yeah, thank you.
Any other
I had a couple
questions?
of questions, if that's okay.
That's great,
Yeah.
John.
Yeah, awesome. It was a great talk. It's just such a fascinating topic, Vamshika, and Amandeep. I had a couple of questions. The first one was just for my understanding, is the assumption of your model that something is already being classified as a cyclone, and then you're classifying, given that it's a cyclone, whether it's rapid intensity or not?
Yeah,
Yeah,
it's
so
correct. Firstly, we know that they are cyclones, and then we are classifying if it is rapidly intensifying or not, using these models.
yeah. And then my second question is actually about this histogram. I'm presuming that this basically the yellow is actually the original plus the augmented, which is why the yellow is always higher there on that histogram.
Yeah.
And I'm wondering, do you have an understanding of why it is the augmentation seemed to only sort of pick out wind speeds in that around the kind of bulk there in the middle? I guess it hasn't it hasn't it hasn't generated data at either very low or very high wind speeds for the most part.
Yeah. So the wind speed generated depends on the actually the rapid intensifying cases that we originally have.
Yeah.
So it is as we see, it is high for this case because there are more RI rapid intensification cases around this 40 knots.
Yeah.
And also here also it is high because it is high between 60 to 80 knots as well. So it depends on the original distribution.
Yeah, so it's just emphasized what's more common in the original distribution a bit. Yeah.
Yeah.
Yeah, cool. And the final question I would ask is, so it seemed, I'm just wondering if in the background in the experimentation, did you sort of vary the amount of augmented data that got added in to try and find a sweet spot? So rather than, because I only saw sort of like the unaugmented experiments plus the augmented experiments, did you do
Yes,
something like looking at,
I
yeah.
think it's uh,
Sorry, was that Rohit or Amandeep answering that? I wasn't.
It was Rohit, I guess. His
He
network
might
might
have
not
just
be, but
dropped out.
yeah.
Yeah. I think I heard a yes. So I'm gathering that there was experimentation in the background that didn't quite make it into the paper, maybe that's about the amount of augmentation, sort of fine-tuning exactly the right amount of augmentation.
Could you please repeat your question? I didn't quite get it.
Yeah, so the idea is, so you've showed here's the data plus the augmentation.
I mean,
I can hear you now, Rohit, if you wanted to jump in. Or I'll continue to the.
yes. So I think yes. Can you hear me?
Yeah.
All right. So I just want to say that the science of data augmentation is quite weak to really. All we know that there's kind of a black box data augmentation process at the moment, because like we have done a lot of in things here, investigating different types of models, ensemble models, multivariate models, things like that. So the data augmentation bit was not really the main focus of the paper, because a lot of effort has been done on other things.
Okay.
So we can only say that data augmentation really seems to help in certain cases. But to say like what actually in the data augmentation process is more helpful, is it curvature of the cyclones in a particular way? Is it a certain group of wind intensity or certain interval of wind intensity that makes it more interesting, or so we need to kind of do some follow-up work on this. Is a interesting topic, and follow-up work generally for data augmentation work, it's like you dump data using GAN or SMOTE or other methods, and that's it, and you don't really investigate why, so I think we need to have projects where we do ask the why question. For example, for such as this, the why does can open the lead in understanding more of the natural phenomena about cyclones and why do they rapidly intensify. These are questions that are still kind of unknown to the meteorologists and climate extreme scientists. They are also trying to investigate it.
Yeah, cool.
So I think so. That was a good question, but I see the effort of the direction of data augmentation in this specific area. There's not that much of work done in climate extremes, but we do think that climate extremes, by the term extreme, basically you mean it's kind of a type of class imbalance problem, right? So, and where there's class imbalance, you need to generate synthetic data. But the thing is, how good is the synthetic data that you can get through visualization of the synthetic data? But the case of cyclones, rapid intensifying cyclones, it's a tough problem. I think it's a very tough problem. It all took us 10 years to really think about this problem, and a number of students contributed, interns contributed, and finally we come with a product of some sort to let us investigate further. So it's a tough but enjoyable ride. And I would like to say that in the area of climate extremes, we need more of this sort of work, particularly in not just thinking about SMOTE and GAN type of solutions to your data augmentation problem, because we can use even ResNets, and other types of models, other deep learning models to create data, right?
Yeah. Thank you.
Right. Um, is there anybody with any other question or comment? So, Amandeep, would you like to say something about this project? Is there anything you would like to comment?
Yeah, first of all, like as Rohit mentioned, it's been I was intern under him, I guess around 2021 till 2022 first quarter, and like I've seen the work evolve myself. Like as we mentioned, like my part, like when I compiled the results, we were using SMOT at that time and SMOT GAN to augment the data, and so it was I'm glad to see that like things have evolved from that, like when Vamshika joined and we have replaced the augmentation thing with the LSTM itself. So yeah, overall I would say it has been, this was my
Yes,
first research project, and I'm glad to be a part of this group and Rohit.
thank you, Amandeep. And thanks for mentioning about the earlier parts of the project. I think some parts are already in the GitHub repository timeline. So I said this project happened 2 years ago, but now I can see that the GitHub says 4 years ago. So, and things have changed. And so,
Yeah.
yeah, we did try SMOTE, we did try GANs, and tried a number of things. It's a tough work. And finally, we were like, okay, and we're not making progress with any of these things. How do we reframe our research question? How do we do things? But thanks, Vamshika. Also, Vamshika was also doing another internship, traveling and all that, and we've been kind of more than a year working on this. Anyways, it's just an example of I think from my other projects, like some things you cannot leave it, you just need to complete it, no matter it takes 10 or 20 years. So it's 10 or 11 years in this project. Yeah, thank you very much, everybody, and we'll continue with the seminar series in the coming weeks.